I'm going to introduce Abby, who's then going to introduce the panel and the panelists. So Abby is a doctoral student at MIT in the Institute for Data, Systems, and Society. We have a lot of reps from that group today. She's working in the MIT Center for Sustainability Science and Strategy, and her research is focusing mainly on humanistic and holistic approaches to data science for climate and energy science, particularly as it relates to environmental justice and urban sustainability. So Abby, take it away.
Thanks so much. Thank you so much for coming to this panel today. What we're going to start with is some just quick research presentations from all of our panelists, and then we'll move into a discussion section. So first I'd like to invite Dr. Arlene Fiore, the Peter H. Stone and Paula Malinot Stone Professor of Earth, Atmospheric, and Planetary Science at MIT to share a little bit about her research.
Thank you. So I thought I would try to give a little bit of a flavor of some of the questions that we work on, but also really giving you a sense of some of the tools and the data sets that we're, especially ones that I think are especially sort of data science, machine learning friendly given the audience. Generally, when I'm asked what does my group work on, the way I sort of pitch it is, well, we kind of sit in the center of these two big problems in environmental science in the 21st century, and that is air pollution and climate. And I should also just be clear that we also work kind of just in one space and sometimes just in the other. And my field is atmospheric chemistry, and what will pop up, if you want to just even go to slide 2, that's fine. But basically, that atmospheric chemistry sits in the center of this. And so, okay, what are these little schematics I've put on? The first is that we are bridging scales from local to global, and global back to local, both in terms of air pollutants that have lifetimes, which means once they're emitted into the atmosphere, how long do they stay there, and many of them are long enough to be transported around the globe. And to make things even more complicated, some of them depend on where you are in the atmosphere. So that makes things complicated. Thank you. Okay, so atmospheric chemistry links two major environmental challenges sitting in the center here. So just to give you an example, one of the big connectors between air pollution and climate involves methane, which many of you are probably aware is a greenhouse gas with a lifetime on the order of a decade. And when methane breaks down in the atmosphere, it produces ozone, which at ground level is a major constituent of smog, so ozone smog, so connecting air pollution and climate. But the really fun part, and what makes atmospheric chemistry so fascinating for me, is that the major sink for methane in the atmosphere is through this thing that I'm not going to try to bore you with too much chemistry, but OH, this hydroxyl radical, which we think of as kind of the atmospheric detergent, if you will, only hangs around for about a second. Okay, so now we have something that is only around for about a second, destroying something that hangs around for a decade. So for those of you who think about how would you solve all this chemistry, right? It's a pretty stiff system. And so, and it's expensive to run. Some of our biggest computational workhorses are effectively running weather or climate models with atmospheric chemistry on top of them. So they're very expensive. So immediately you can see why it's nice to have cheaper versions of kind of emulators, if you will, that can represent some of the connections, and we can potentially probe these to understand processes without having to run the big models as much. And so there's some of that going on in our group. We also like to ground our models in real world observations. And so we basically kind of use whatever data we can get our hands on from many observational platforms, including airborne, including ground-based networks, as well as satellite data. Okay. And with respect to satellite data, in my field, we are in, I would say, the midst of a revolution in our ability to retrieve information about atmospheric composition from space. And for several decades now, we've had satellites that are polar orbiting that basically give you kind of one snapshot a day of what's going on globally. And more recently, in 2020, the Koreans launched this instrument called GEMS, and then in 2023, staring over North America, this kind of domain shown here was this TEMPO, and thank you. Our colleagues over at Harvard in the Center for Astrophysics are the key retrieval team for some of the gases that are now streaming back to us in terms of the column abundance that's retrieved hourly during daylight hours, as long as there's no clouds. And so there's a whole, I could talk forever about that, I'm sure, but basically these are now big data sets, even bigger, that we have to think about. How are we dealing with, what are the uncertainties, how do we interpret them, how do we use them to learn about the processes that we care about, which are the transport and formation of air pollution in this case. And so Madan Tao, who's in the audience here, has done a lot of work with both those older satellites that give us data going back decades and this newer satellite. Okay, in the interest of time, I'm going to stop there, and I think I won't talk through this because I think we're going to have an opportunity during the discussion, but I wanted to just mention that I have been fortunate to be part of this NASA Health and Air Quality Applied Sciences team, where we work with stakeholders in the air quality management and public health communities and try to think about how do we translate the information that we can get from space and Earth system models and et cetera into users who are interested in making decisions based on our best understanding of these processes. So I'll stop there. Thanks, everyone.
Thank you so much. So next we will have Dr. Suchi Gopal, the Professor of Earth and Environment and a core faculty member at the Institute for Global Sustainability at Boston University.
Thank you so much. Talk is going to be, I can actually project my voice. My talk is going to be more oriented towards societal adaptations and vulnerability, and I hope to throw more light on the developing South, because we have grants both in Belize, Indonesia, and several work orders in Kenya and Africa and India also. So the first slide I wanted to show is, I want to set the conceptual framework in order to talk about the two topics that we were given today, and the best way seems to be to use the Stockholm Resiliency Institute's planetary boundary framework. This particular framework sort of gives you some understanding of the planetary status as well as the resiliency of the planet. So if you escape any of these 9 boundaries, it is surely going to create a lot of problems and havoc. So far, 10 years ago, they said we crossed 6 boundaries. And now they say we've crossed almost 7 boundaries. And these boundary crossings vary from place to place. Be working in Indonesia, and there it is like different boundaries, set of boundaries than compared with the US. So you may ask, what are these boundaries and why are we sort of fixated on this? These boundaries sort of explain the interaction between many systems in the planet. It is not just climate being just, all costs in the atmosphere and touching the planet. It's also all the things in terms of ocean acidification, land systems changes, freshwater changes. All of these act in unison in order to create these problems, especially impacting societies. So I won't spend too much time on it, except to say that during our discussion, we are going to be talking about the so-called triple burden or double burden, which is societies being exposed to high exposure, high sensitivity, and low adaptive capacity. 50% of the world's population sort of pays for 75% cost of what's happening in terms of climate change. These numbers are sort of well established now by the World Bank as well as the UN. And we could talk a bit more about it because they cost 10% of the pollution, and they're bearing the cost of what's happening on the planet. So there are many different data sources that are available. I sort of work in many different areas, including fintech and finance. I became interested in finance, sustainable finance, because money talks, really. We were giving advice to many people in places like Cambodia or Vietnam or Indonesia. Nobody wanted to listen to us. But if you sort of talk about investment and a bank loan from the World Bank or from a Bank of Asia, then they're interested in talking to you. So these investment opportunities have created a lot of opportunities for countries as well as people on the ground to make use of it. So we could talk about it when we sort of talk about our climate data and spatial resolution and temporal resolution problems. So I can come back to it. And Arlene talked about quite a few of the satellites. So the planetary health sort of data comes from satellites, on-ground measurement, as well as you could also use social media at this point to find out what people are up to. And that was the first panel that was talking about democracy and using social media. There's also a lot of other, registries, including hospital discharge data and so on. And of course, they're not going to share that with you openly. This is especially to do with heat deaths and the so-called experiences that we have now with increasing heat waves, especially in Europe and North America. So proceeding on, there's a lot that's going on in terms of these pyramid effects of air pollution, as I said. And if you look at a map of the US, you can see that the dark blue areas, that's in south, in Harris County in Texas, as well as along the coast, these experience high particulate matter and low income. And this is one of the topics that we're going to talk about when we do our discussion. So as I said, there is a lot of different platforms that we can use to find out about climate risk at an asset level. So one of the problems we are going to talk about is scaling and spatial scale, and how do you downscale from using satellite data. So that would be the topic that we'll cover there. So the last slide that I wanted to talk about is the fact that you can pay farmers to grow crops and to maintain their farms in perfectly good shape, or grow trees and so on, and you can give them money, and this is all on blockchain. This is a big sort of improvement in terms of sustainable finance, and I'm happy to talk about it if anybody wants to do it. And it's blockchain technology is very important. And I just finished a book in 2024 on this topic, and so I've given you the QR code. Thank you.
Thank you so much. Okay, our last panelist to present will be Dr. Desiree Plata, School of Engineering Distinguished Climate and Energy Professor and the Director of the Parsons Laboratory at MIT. Here you go.
May I stand here? Thank you. So I grew up as something that today's internet would call a free-range kid, if you can't tell from the haircut and the slight bell bottom. This is about 40 years ago in Portland, Maine, about 100 miles from here. That little red dot marks my grandparents' house, and I would go around this neighborhood, and I would hear stories, by myself, talking to people in the funeral home about diseases that people were encountering in their daily lives. And it seemed like every other house had a cancer or a neurological disorder, and really young people. I was super surprised by this. And so when I was about 8, I was driving in the car with my mom back to our place and asked her, there's got to be something in the air and the water that these people share that's causing this. And she was like, nah, don't be crazy. It's the power lines or something like that. And so this intense concentration of disease actually was something that was related to a Superfund chemical contamination site that was designated sometime when my mom was in college, but she had missed it because it was like buried in the Sunday paper. Nobody really knew what was going on. That plume that I'm showing there is the trace of trichloroethylene. I call it my nemesis compound. It's and my aunt lived right in the middle of that brown trace. My aunt later developed cancer, and when I was in graduate school, passed from that. But I was really committed because of that experience and event. She was one of my best friends. She had 3 young kids at the time, I was really committed to trying to change this. Now, it turns out that the person who ran the chemical disposal site was my mom's high school boyfriend's dad, right? And all his kids got cancer too. And he ended up moving and leaving because he felt so bad about what he had done to this community and such personal responsibility, even though he was doing exactly what the Environmental Protection Agency told him to do with that toxic waste at the time. And so this was all happening for me when I was in graduate school, and I said, okay, these are good people running these big industrial companies. They need help understanding what to do best, and that should be the role of a modern environmental chemist or environmental engineer. And so I really committed my career to trying to understand these complex industrial processes and walk in the front door of companies to say, how can I help you do what you're doing better and also protect the environment at the same time? And so this is just an example of, I process nowhere near the data the two ladies who just spoke to. This is like a 15-point reactor that we built about 10 years ago. This was a huge high throughput, high pressure reactor that we used in the study of hydraulic fracturing transformations. It turns out that we can know what type of geophysical conditions and chemical exposure is occurring around the country to be able to predict a likelihood of concerning transformation products. So we can say, if we've got 1 million wells in America near many millions of drinking water sites, which one should we prioritize for actual analysis and maybe providing clean drinking water to the people living there? Now, I'll just give you a couple of other quick examples of the type of work that goes on in my group. This is, the undergrads always scoff when I say plastic pollution is my favorite pollution. It's my favorite pollution because it's the most Instagrammable of pollutants, right? You can see this with your eyes. Now, we've been swimming in a sea of organic chemicals since really the 1970s or so, but you couldn't see it, right, with your cell phone camera. And this you can. And this has brought immense attention to climate change as well as industrial pollution. And so my group likes to ask questions about, okay, what types of chemicals are being formed from those industrial materials in the environmental system, and can we actually follow those transformations? So now we actually, because of advances in analytical chemistry, don't need to do high throughput experimentation. We can watch thousands of molecular transformations at the same time. Now, there's lots of detail that goes into that, and it's not as precise as I would like it to be, but we can start to look at what is the dominant, say, transformation products. Are those things going to be toxic? So when we make one industrial molecule, we now know how long it's going to live in the environment or what it's going to form. Nope. So we can also use this type of analytical chemistry to generate larger physical chemical data sets. So I don't expect you to interpret all of this, but if there's something called the octanol water partitioning constant. We can use that as a proxy for how a chemical is going to go into your body or somewhere else. In the environment, and this plot on the bottom shows you the measurements of those partitioning constants against what would have been predicted from some of these computational tools. And I like to say, I can't make this joke here. This must have been developed by one of the Harvard kids. Sorry, Arlene. Because if it agreed, you'd be on the one-to-one line. No, obviously we respect our colleagues there. They do some great work. But what's good about this is that now that we have this good, real physical chemical measurement, we can go back and train all those models to improve, right? We're now generating physical chemical data at much higher rates with much higher intercomparability, and that's really important. And so the vision here is if we can know from a chemical structure, what types of reactions are present in the environment, we can know where they're going to go, potentially what it's going to turn into. That gives us the transport and the transformations. And if we work with some of our partners who study toxicity and apply some machine learning to this, maybe a chemical designer can say, this is what I'm making, what's going to happen to it out in the Earth system, and is it safe? That hasn't been the status quo in America. The status quo has been to actually just use it until somebody observes a problem. And I don't know how you all feel about that, but I find that a little disturbing. So I won't go through these slides because I think I'm at time here, but I will maybe tell you that we need your help. And this is, the greenhouse gas emissions profile, 51 gigatons annually. This is 2019, where that black line breaks apart from the red line. We weren't doing terribly well before recent administrative change changes in the United States. So don't be discouraged, right? Well, there's lots to be done. It is still the case that there's lots to be done. And these are problems in the physical world. In order to close this gap to that 2-degree potential, I got a whole list of ideas, and all of these ideas need you. And I don't care if you're a mechanical engineer or a data scientist or a social scientist, we definitely need your talents applied to these problems. And within each of these, I could enumerate lots of different sub-problems. So if you're looking for problems to work on, I didn't get enough lifetime, and I'd be happy to help you talk through those. So I'm going to skip through all of our work on agricultural waste. Here's just an example of the transition. This is our greenhouse gas emissions today. This is what they need to be in 2050. This is our carbon removal today. This is what it needs to be in 2050. That's a dramatic change that's going to occur in your lifetimes, and we need your help with that. Thank you.
Do we have a second mic? Do we have 2 mics? Okay, so we're going to transition to the discussion portion of our panel. Thank you so much for those presentations. I've got a second mic here that you guys can. There you go. So as we saw, environmental research is very applied in nature, and all of you talked a little bit about this, but I was wondering if you could share some of your experiences with transitioning your work from in the academic sphere to policy and industry to have real-world impacts. And anyone can start.
Okay. So yeah, I mentioned in my last slide, kind of tried to illustrate a little bit of a schematic of just an example of how we can transition kind of work that's maybe more on the academic side into actual real world use. And one of the things that is maybe worth mentioning is that in the US kind of air pollution world, there is a very clear regulatory framework for implementing national standards. And so a first kind of, I guess, lesson I would say is you have to understand the framework that your people making decisions are operating under. And that framework really relies heavily on gold standard data, so kind of certain types of instruments that are monitoring air pollutants, as well as certain models that are approved for regulatory applications. That said, there are ways that other data sets and models can come in through weight of evidence in some of the kind of regulatory/legal applications of things. And so one of the reason why I'm giving you all this background is because it turns out that one of the parts of the process is that there are these periodic reviews of the scientific basis on which the standards are set and then implemented. And so there is a clear sort of path of, scientific or research publications to inform policy and decisions in that way because they need the rigor of peer review to include them in citations in some of these regular assessment reports. And I would say it depends on your sort of problem, but in the environmental kind of application world, there's a fair number of problems that have structures like this with regular assessment reports, whether it's international or national. And then the idea, though, what basically we were doing was, okay, we're kind of developing a way of incorporating satellite information kind of into a problem or a process that the air quality, using it to provide information that the air quality managers needed, and then working with a group of air quality managers who are actually using that information. And then the scale up part is kind of like, okay, once one group has found this particular explanation, sort of recipe, if you will, or blueprint, whatever your favorite kind of analogy there is, useful, then why don't we talk to kind of the next circle out and see whether they can actually follow what was done and implement it themselves. And so that was kind of our beta testers, and then eventually we would try to make kind of technical guidance documents or use case examples public so that anybody could access them. And so that's kind of one example process.
Sure. So it was policy and industry, right? Like how we get impact. I think there's like it depends. There's certain cases. So I'll just maybe walk you through a couple examples. So I'm the director of the Climate and Sustainability Consortium at MIT. We work with big global corporations who share common sustainability and climate problems, and we try to help them discover, like what are the commonalities and map that onto potential research questions we could answer, and then work with them to pilot potential solutions in the second phase of that work that they might incorporate into their own policies and practice. So that's like a real privilege to get to talk to these big decision makers. And altogether, I calculated we're about 2% of global GDP, and I feel pretty good at that. Means if you can approximate it to emissions, maybe we can impact about 2% of global emissions. And so the other thing that I do is I'm on the phone with Washington a lot. I was in the last administration. I have been with some frequency in this administration, really on very different topics. But I try to always take those phone calls. And much like Arlene articulated, a lot of what we're doing is translating the current state of the science and scientific findings into, first of all, just common language, but then also into something that those stakeholders might care about, like trying to understand jobs creations or economic value. Now, that's not my area of expertise, but again, I'm lucky to be able to reach out to people who might be able to help make that translation. And often they're doing that in the congressional staffers' offices anyway. And so that's been a real joy to kind of see what their day-to-day is like and translating what I care about into something that they and their constituents care about, or thinking about what they can actually get through law. And then the last thing I would say is that if a technology is really new and different, there's not going to be a receiving industry to go and implement your thing. And I would love to stay in my office and not have to go spin out companies, but that is not the luxury that I can enjoy, right? Because that's hard, starting a company. But often, if there isn't a receiving industry, you might actually have to engage in that. And oftentimes, there's nobody better than you, the person who invented the technology, to go and try and scale that technology out into the real world. And hopefully you can come back to your office and sit with your paper when it gets to a certain point. I'm not quite there yet, but I'm dreaming of that future.
So I would like to sort of talk about the UN Sustainable Development Goals, because like I told you, most of my work is in the developing South. And we are now working with the country of Belize, where they want to invest a lot of blue bonds. And blue bonds are to supposedly helping them with managing their mangroves that provides natural resilience against storms and against sea level rise. And this is the same in Indonesia, the other country I work in. So we work with people on the ground, with scientists on the ground, and universities are partners to make this happen, to identify the right spots in which to invest money, because you don't want to sort of go in and choose a spot that's at risk anyway. So there's a lot of climate metrics and the so-called DMRBs, which is the MRB is the measurement, metrics that everybody seems to like, that we use a lot of using satellite data and other data to talk about it and make it happen. And like I told you, I have a company which was actually came out of my university faculty grant, and that's to do with this aspect that I told you, which is on sustainable finance. And that sort of deals with how do you help individual farmers on the ground, and how do you make them sort of, get into this economy and make use of the capital that they are provided by the likes of Delta or some airline company that wants to get carbon credits. The biggest thing that has to happen is that we need to have a carbon currency. And we are not there yet. We are in cryptocurrency. But if we can trade in carbon, it would make a big difference. Because the value of carbon changes the way we look at finance and changes the way we are going to value the environment, unfortunately. Right now, the price of carbon is around $70 or $80, I think, in Sweden, the highest. California has a price on carbon. In the rest of the US, as you can guess, the value is zero. So these frameworks have to change, and we really need to do a better job in helping people everywhere on this planet to reach their goals. Otherwise, we are going to see a crisis, a planetary crisis, and we already begin to see this in migration flow patterns. It is not geopolitical only. It's not people sort of fleeing. Nobody wants to leave their home, their ancestral houses. They want to stay in their, homes, but they're forced to leave because there's nothing else that they can do. And this is going to be true of our plight in the next 10 or 15 years. We already see this happening. And we need to be in a better position to address these problems with data science, with AI, and all the things that we've heard this morning already. Thank you.
That is actually a really great transition to what I wanted to talk about next, which was how we can democratize the practice of environmental data science, because having communities be able to work with their own environmental data is crucial to ensuring environmental impact. So I was wondering, how can data scientists and how have you empowered local populations to make decisions using environmental data for their own communities?
Oh, that's really fun. I think that, so I have this dream where you actually go in and train local communities to generate their own environmental data. So, like where do we have big data, right? We know where you've been everywhere since maybe you could, walk around autonomously with a cell phone. We know everything you've bought. Most of what you've eaten, is recorded if you paid with your phone or your credit card. That's like big data, right? Big data. We don't have that luxury in environmental chemistry and environmental systems. And I would love to conscript like every human on planet Earth in the generation of that data. And I think it solves some problems. So as Suchi was saying about giving people access to improved incomes and improved quality of life, this is a huge opportunity. This economic transition that's going to occur is a huge opportunity to lift up populations. Now, it actually could solve some really key problems, and I'll give you an example. Like, so let's, and I can come up with a couple of them, but one may be in global mining, right? So everyone's probably aware, like we need 4 times the amount of copper and minerals that we've ever mined before in order to meet our modest renewable energy goals and electrification goals. We know where a lot of that copper is, but it happens to maybe sit on First Nations lands, or maybe the people who own or who live in the community aren't actually eager to see the mining companies work on those properties. And so how do you reconcile that? Now, I don't want to pretend like I've worked deeply in this space or solved this problem, but one of the things you might consider doing is actually training the local people to collect the data on their air and water and soil and sediment quality. So then they own that information. They don't say, trust me, it's fine. You say, you can show me that it is fine. And this is really starting to happen because analytical tools are becoming more and more robust, easier to use, lower cost. And what I really love about it is it provides access to higher pay careers in the STEM workforce all of a sudden. And so we need lots of workforce to make that transition I just talked to you about. So you're kind of hitting that bucket. You're maybe doubling their income. You're giving them access to that data, and you're saying, let's be partners in this data generation. And then, of course, you've got to kind of back the data informatics system, and that's ironically become the easy part now, as interesting as that is. And then I would just like maybe disclose that there's a ton of legal implications to that. Like some mining companies have and governments have signed contracts that make that impossible. And so there are some political hurdles that would need to be navigated to see this through. And I can talk about some other examples if interested.
So I want to give you like 3 examples, one from the US. My colleague, Dr. Nathan Phillips, does a lot of work in methane gas leaks, which is the leaks that are happening all over Boston, all over the US, in any major city in the East. And we worked on a project called Smell Something, Say Something, because we had to train people to smell methane gas leaks. And they didn't know what it even smelled like. So we had a project that was funded by the National Science Foundation, and we were training middle school kids to do this, right? And then they would say, they would ask their parents to shut off their car engines because they would go, oh, that is also methane, in their, way of thinking. Yeah. So it was very good to work with community that way, and we still continue that work. We also work with a lot of different organizations in the city of Boston, educating them and making sure that these communities are able to participate in these activities to reduce the dangers posed by gas leaks. And even last week, there was some explosion someplace. These are like deadly. People could get killed just because of gas leaks. So the second issue that I wanted to bring in is the rise of the data centers. All over the world, there's so many data centers. So if you want to train people, one of the things they immediately notice, and this is especially true both in the US and elsewhere, is the water and electricity bills going up or going down. And they take pictures of what's happening and the noise they record. This morning, as I was driving in, I was hearing that there's a lot of noise in one of the facilities that's going up in Massachusetts. People are complaining. So what do you do about it? There has to be some community action, and communities have to be taught how to do this, and they can make their voices heard, especially on social media. Since at this point, we don't read newspapers, we read social media. So it seems to be a good idea to do. So there's a lot of different examples all over the world, even in developing South. And I worked for a project on Microsoft many years ago that was funded by the Gates Foundation. And that was, how do you sort of get people, women especially, on noticing the quality of drinking water or something and marking wells and so on and so forth. And they had no way to read or write, but they could take pictures and share. So we were giving them cameras so they could take pictures and post it, and we would know what was happening. So there are many ways to get at this data and have the community involved with you as you do your work.
Yeah, I'll maybe just add a general point that is kind of, there's the bottom-up data collection and then the sort of top-down view that we get from some of these satellites, out there. But one of the challenges is these are generating really large data sets. And so even though a lot of it is public, how do you make it accessible? And so I think that just speaks also to the need to kind of process raw data in ways that then gets it to something that is usable, or the quantity that is of interest to different communities, but also providing kind of public-facing visualization platforms or things that kind of layer not just that one data set, but with other data sets, so you can kind of start to get a sense of different risks or potential hotspots. And so I wanted to mention some of the screening tools that I know Suchi had mentioned on her slide, one of her slides. And then also just, I think many in this room, my guess is, are involved in kind of developing different GUIs to sort of put different data sets together. And so I think that kind of work is also incredibly important, especially if you can start melding that bottom up and top down view.
So similarly, when we're talking about data collection in different places, different spatialities, currently urban and rural environments have very different environmental monitoring capacities, which has huge equality implications. How can we address these inequalities in data availability across these different scales of urbanity?
I was just gonna let you go first. This is a hard question. If you want to go, I can talk about. You want?
Yeah,
Here,
you
go.
talk about
you
your.
go, and then I'll go. Yeah.
So there's, this is more to do with GIS and spatial analysis that I do a lot of. So there is a lot of information available for especially countries like the US. But, most people live in the cities, and so there's a lot more census blocks. So the census hierarchy pretty much guides our analysis. And there seems to be like big, large blobs of, rural areas in Kansas and Nebraska and so on that don't get counted at all. And this actually became very clear to me when I was trying to study opioid addiction in the country. I could not get data at the census tract level. I could get a lot of data for, the East, the metropolitan areas, East and West Coast and so on. but not in the dead center of the country. It doesn't mean if I were to just read that and take it to be the God-given truth, I would have said, oh, there's no problem of opioids down in the rural countryside. And that's a wrong decision to take, because it's the data, the way we collect data, the way that we sort of attribute things, and the less importance that's given to rural areas. And as you can see, many people are now fighting back and saying we need to do a better monitoring of all of the country in equal and especially for public health. This has become a huge problem. We really don't understand, the inequities, especially in health, in the rural, Appalachia, for example, or the rural Midwest. And we see this every once in a while in some program, and we think about it and say, why don't we have data there? We simply don't. And that's the way data is normalized and collected, and there has to be better ways of doing this.
So I might just jump in there and add on, because I think when you start talking about health data, and this is not exactly my area, but we collaborate with people in the public health sphere, is there's a lot of privacy concerns. And so to the extent that you can aggregate up that data and sort of protect individual privacy, right, then more of that data can potentially be released. But then if we start thinking about populations in kind of rural versus urban, right, it sort of just exacerbates this whole issue. And I would also say that similarly, generally, we're monitoring if air pollution is your focus area. We have much more information about what's going on in urban areas. And similarly, if then you're trying to think about a top-down constraint, for instance, satellite data, not to sound like a broken record here, but the places where you tend to have more information to kind of understand how to translate what we get from space, which generally is we're not seeing the ground, we're kind of inferring from what we see for all of the concentration in the column, kind of looking down, what does that mean for the air pollution on the ground? So by the way, that's also a place where machine learning, et cetera, can come in and potentially help. But I think I guess I'm just speaking, there's lots of ways that biases and what we think we understand from our data can come into this picture. And so it speaks to the need, I think, for workforce who understands how to think about what we're not able to see in our data, but what we might be missing, and also to think about what I think of as sort of external validation data sets. So are we out there collecting independent measurements in both rural and urban areas that can help us to kind of get a better handle on those biases, and then use, whether it's satellite data, machine learning models, other kinds of models to fill in. And we do in the air pollution world use models a lot, but again, you want to evaluate those, whether those are physics and chemistry based models or statistically based models.
Yeah, those great answers. I've mostly thought about this from the drinking water perspective. So if you are serviced by a well, you might have your water quality assessed for a small number of contaminants when you sell the house or when you move in, and then you don't actually have to ever measure it again. Whereas if you are serviced by a public drinking water supply, your water is really heavily monitored, at least at the distribution point, and then also randomly throughout the year, almost quarterly, at other distribution points. So other homeowners are having their water tested. So there's lots of eyes on, and this is like a flow down from the law, right? It is your right to not test your well water and drink it if you want to. But the municipality has to ensure your health and safety. And so this creates a huge disparity that is people are starting to overcome. Now, those water quality assessments, it's like pH and some ions. You think PFAS is routinely measured? Like, no, it's not, right? And lots of contaminants are not routinely measured. And so the way around this, right, is again like conscripting lots of people in assessment and measurement. And so I begged my students for years to build build a mail-in program. I'm like, somebody start a company where people mail in their water and we give them measurements and blah, blah, blah. No. And, but one of my friends did it, and I'm super excited about it. So you can send him $250 and he'll and he will tell you all the PFAS that's in your water and everything else. And then he's going to have the access to that data, just like 23andMe, right? Spit in a tube. Thank you very much for your genetic information. You can pay me for it. And so like that's it's kind of wild, right? But people build these systems to amass this data. And the point that Arlene made is one that like I spend a lot of time thinking about right now. That story I told you about my family, like that town, they experience that as shame, right? They don't like to talk about that. They get really upset with me when I mention it because they're worried about like, what does it mean for them personally? Are they damaged? What does it mean for their property values? So when we've gone out and measured, drinking water in many hundreds of groundwater wells across Appalachia, we had to be very careful to make sure that that information was not disclosed, right? But we want to amass the data. And so it actually takes, it's a pretty laborious work, right? Like we sit down with them and tell them what their water quality is, and we help them try to understand that. And then we do something similar for public drinking water supplies, but it's kind of night and day, as I'm sure Suchi sees in her work as well, working with those two communities. I just want to make a plug for anyone who's interested in ground-based monitoring. For Amy Miller's group at Northeastern has a great air quality monitoring program where they're doing some really interesting work to try to assess the distribution of ground level monitors and how those might be overrepresenting particular populations. And then Rebecca Fry at the University of North Carolina, Chapel Hill has a groundwater well monitoring database that she's amassed that basically jiggers the data to try to protect privacy and health. But those are two great places to go if you're interested in applying your skills there.
So we've been talking a lot about data in different communities and different types of data. So I wanted to ask, local knowledge of the environment is not always written down or searchable. So how does local lived experience and tacit knowledge complement or maybe complicate our work as data scientists? And how might these types of informal knowledge be impacted by future AI research methods?
So I'm just looking at my student Mira, who's just come back from Belize. So she sort of was looking at verifying and validating the labels using AI machine learning system for land cover classification that's normally done. But her approach was ecosystem classification. The two things are different because in general, when we use Landsat or Sentinel, we are always classifying the so-called land cover. We don't do land use, but we do land cover. And she can explain to you what the difference is. And so the ecosystem monitoring and the systems services provided by the ecosystems are very difficult to enumerate. If you were to count the number of services nature provides, 1 year it provides $1 trillion worth of ecosystem services. We don't count that because it's free. So you can look out of the window and say, oh, it's so beautiful outside. That's nature providing you the beauty. What's the money you owe it? So anyway, we are trying to sort of check this out for Belize, and she found that the valuation of ecosystem services is so different for people, local stakeholders, NGOs, commercial tourist providers in Belize, because everybody now has an Airbnb all along Placencia, all along Key Cocker, all along the coral corridors. And so it was very important to understand the valuation, that it's not the same because local people view it differently. And this is something that we really need to understand. And there's also some things with regard to AI that I would like to talk about, but I would pass the mic and should I do the AI part? So the AI part has become very important for public health. And this is the so-called idea of sovereign AI. Countries of the developing South are more concerned about looking at their development trajectories. They're not so concerned about what the US is concerned about, which is privacy, security, and things in AI that we had talks this morning. It's going to influence the way we vote and things like that. So if you were to look at the conference that India had recently, about a month ago, where there was a lot of, political statements made on what AI is capable of. One of the things that was fascinating is to preserve the local knowledge and to have sovereign AI such that it's in every language in India, which has 144 dialects and many written languages. So they need to have people sort of communicate and give the health information more locally such that every voice is counted or heard. So sovereign AI is something that you all ought to be thinking about, because that's like the future. Every tribal person in the places I work in places like Indonesia and Belize, there's so many tribes, we don't even count them. And it's the same thing for tribes of North America. It's only recently the census has put out a tribal map, census map. So you can think about including voices which are not heard of most frequently, which is, these people who are not educated, who are left behind, who should be involved in all this inclusivity that we are thinking about, because every voice, I think, ought to be heard, and public health is of concern globally for everybody, and that's according to the UN mandates.
So how do we incorporate local voices, right, is the question. I got so enthralled with what she was saying. I was like, oh, that's right. I think about the disparities in time and kind of time scales. So, in science, we want to move really fast, right? We want to make our discoveries. In business, they have to move quarterly or they're going to get in trouble. And I think in this like kind of cultural discovery process in social science and anthropology, it's slow, right? Like that work is actually slow and it requires time. And I think it requires time because you have to build trust. And I think building trust mandates authenticity. It mandates a real person being present, and it mandates relationship. And relationship takes time to develop. This is a very basic human thing. I think it's present across the animal kingdom. We need to have real relationships. So that's hard, right? Like I was not born with any amount of patience, and I have tried to think through this because I definitely want to respect people's culture and hear those voices. And I think so I've tried to do this by making sure I'm working with really talented community engagement people who have done this as a practice. I am often sourcing those people from those communities. I think that's really important because obviously it was helpful if you have somebody who is already trusted by the community and understands the culture. When I, first started learning about AI tools, I was like, oh, maybe this can help me understand culture all over the world. And I can have projects everywhere. And I'm going to send all the MIT undergrads to go do them. And it's going to be great. And I was like, that is so dumb. And it's actually not able to capture that, right? You really need the participation of local people. But if you can get that, like the implementation of solutions, the creation of solutions, that co-creation is going to be so much better and so much faster and so much more transformative. And, I remember I was asked by a researcher once, like, how do you get these industry people to talk to you? How do you get these big industrial dairy farmers to let you into their place? And I was like, I wear boots, and I realized I forgot to change my shoes when I showed up here. And I wear boots, right? Like I try to learn about their culture before I go and make sure that I can be respectful of that culture. It's very clear that I am an outsider, right? Like they know that I'm coming, they know my profession, but I try to make sure that I am at least helping them see me as someone who's not that different from them. And I think that that's really important to try to speak across boundaries and show that mutual respect in order to get, we should ask you to answer this question. But so anyway, just making sure that you're involving people in the participation. And there's a great professor here at MIT, Professor Janelle Knox-Hayes, who does some of this work and has a whole platforms and toolkits for co-creation with local communities.
Thank you so much to our panelists and everyone for coming and listening. This was a really fruitful discussion.